I'm doing well. How are you doing? Very sporty.
Yes, like it. I think next to your presentation, we are going to eat tacos with
I want
Alejandro, I think.
absolutely. I'm joining 100%. Don't leave without me. So, wait, should I be signing some documents here? So maybe I'll do it now since we have a minute. And silence my phone. All right.
Hola, ¿qué tal? Buenas tardes a todos. Para la gente que está en Zoom, comenzamos en 3 minutos. Gracias.
Empezamos en 3 minutos.
There are already people in Zoom.
Muy bien. Or actually, in 3 minutes or 2 minutes we have. But clearly people are still outside. You can actually, I'm afraid if I turn it off, it will be. it work? Yeah, it works. Fine. Seems like, yeah, it works.
Ok, bueno, vamos a comenzar. Hola, ¿qué tal? Muy buenas tardes a todos. Bienvenidos a otra edición más de nuestro coloquio Acadio Poveda. Antes de comenzar con este coloquio, me gustaría nuevamente invitarlos a todos los presentes y la gente que está en Zoom también a que se autopropongan o a que propongan candidatos para el coloquio. Sabemos que estamos a punto de terminar el semestre, que ya casi salimos de vacaciones, pero para el siguiente semestre todavía tenemos bastantes fechas disponibles, entonces si alguno de ustedes tiene un trabajo que quiera mostrar, algo que acaba de publicar, algún colaborador que quisieran proponer, pues con mucho gusto nos gustaría pues recibir sus solicitudes o sus propuestas. Dentro de poquito les vamos a hacer llegar una liga con un Google Drive donde tenemos las fechas que ya están ocupadas para el siguiente semestre, para que puedan ver cuáles están disponibles y entonces así proponer a la gente o proponerse ustedes para poder dar una charla. La verdad es que nos gustaría pues saber acerca de su investigación y tener muy buen coloquio, buenos coloquios para el siguiente semestre. Y ahora voy a cambiar a inglés. So I'm going to present our speaker today, Dr. Maciek Wielgus. He is actually working at the Max Planck Institute for Radio Astronomy in Bonn. He got his PhD back in 2016 at the Warsaw University of Technology. And he is currently a research scientist, as I already say, at the Max Planck Institute for Radio Astronomy in Bonn in Germany. He is interested in radio astronomy and in the physics of compact astronomical objects, such as neutron stars and black holes. His work focuses on the Event Horizon Telescope project, for which he is involved in dataset reduction, analysis, as well as a bunch of theoretical and observational sub-projects. And today he's going to talk about a very famous black hole, the one in the center of our galaxy, Sagittarius A star. So, Maciek, thank you very much for coming today, and the floor is yours.
Muchas gracias. Voy a hablar en inglés, pero mi español no es muy bueno. Okay, so thank you for this very kind introduction. And let's jump right into it. Let's start from this picture. This is quite a large angular scale image of the galactic center. So if you look toward the constellation of Sagittarius in radio waves, this is what you will see, particularly if you look at spectral index. It's not a direct image, it's a spectral index. But it highlights what a mess is the galactic center. You can see there are so many structures there. Some of them look quite weird. There is this filamentary structure going on, which is the light on, things like this. The brightest compact in Sagittarius A star is this feature called Sagittarius A. And to give you the idea about the angular size of this image, a full moon would be something like this. So it's really a kind of macroscopic feature on sky. Now, however, if we dive into this complex and if we zoom in a couple of million times, so we need indeed a huge magnification, you will see that. And I will be talking about this donut-like shape and what did it teach us about the accretion physics and about black holes. Right, so another way to look at this very complex structure of the galactic center is this diagram. It's kind of more easy to digest because it is a cartoon and not an actual image, but you can see again how many different features live inside this very inner part of the galaxy. So this is the plane of the galaxy. There is one disk of stars on kind of extended size. They are going counterclockwise. There is, however, is sort of a clockwise set of stars just next to the Bondi radius, so kind of in the realm where the gravity of the black hole is actually winning and ruling them. And even deeper, there are those S2 stars, so-called, for which there was a Nobel Prize in 2020 for tracking their motion and inferring the mass of the central black hole through the movement of these S2 stars. So these guys are actually deep inside this center. I will draw your attention to this spiral-like feature because it will come back a couple of times during my talk. This is what we call a mini spiral. These are few limbs of gas trickling into the galactic center slowly and emitting weak thermal radiation. So this is not a talk about the history of discovery of Sagittarius A star, although it's quite an interesting history, and one could deliver a really fun talk just talking about all these steps. But I only want to point your attention to one thing in this slide, and this is kind of the science acceleration that have happened. So the first row, everything you see happened between 1974 and 2011, so kind of long time scale. And the entire bottom row happens between 2015 and 2022. And we already have new results not shown here about polarization that I'll be talking about, so we should already extend it. So this is kind of showing you the acceleration of science that we are experiencing these days. This is not a history talk, but there is some bit of very early history that is kind of interesting enough to sneak into this science talk. So I will very briefly tell you about the history of the detection of Sagittarius A star. So this story really started in the 1960s. And in the 1960s, people for the first time realized that distant quasars probably harbor supermassive black holes. So then there was idea propagated mostly by Lyndon Bell that nearby galaxies, which are not powerful quasars, could be kind of old quasars, that maybe they were quasars once. So maybe there should be supermassive black holes in nearby galaxies, and in particular in our galaxy, that would be like a remnant of a dead quasar. So there should be not very active supermassive black hole in the center. So when kind of a race to detect supermassive black hole in the center of our galaxy started, it took many years. It turned out that, well, you need resolution to dig up this sort of signal. And the first successful detection that seemed to confirm this story of dead quasars in the center of galaxies happened in 1974. You can see what did they mean by compact? 0.1 angular arcsecond. Now we know the size of the feature, this compact source is about 50 microarcseconds. So it's many, many orders of magnitude more compact than than the upper limit from the first detection. But of course it needed time, technology, developments to be able to see that component. But it's another quite interesting episode, which is how the Sagittarius A star, the supermassive black hole in the center of our galaxy, got his name, and in particular the star to its name. So at that time, people were still thinking very carefully about this dead quasar theory, and at some point they resolved this sort of feature. You already remember this spiral feature. This is our familiar mini spiral, the gas slowly trickling into the galactic center. However, if you don't know more, you don't have enough measurements, you can easily confuse it for like spiraling jet. So that was the interpretation from 1982, that okay, we have this dead quasar remnant somewhere here, and we also have some residual of a quasar's jet. This interpretation turned out to be entirely wrong. However, it was considered very exciting in the beginning of the 80s. And to highlight this excitement, there was this star added to the name of Sagittarius. So this star really means that the scientists are excited. It's not that the source is excited in any particular way. This source is actually not doing all that much. And this is how the name happened. So this was kind of a little bit of history. And let's jump these 40 years forward to the best resolving telescope we had at our disposal today. Event Horizon Telescope. It's a global millimeter array of telescopes. you need resolution to see the feature like this tiny black hole in terms of angular diameter in the sky. To get the highest resolution, you can only beat the diffraction limit in two ways. You can make your aperture larger, so it means you can get a telescope as big as the Earth. This is pretty much the limit unless you send a bunch of radio telescopes to the sky. And then you can change the frequency. So the shorter the frequency, the shorter the wavelength, the higher the frequency, the better resolution you get according to diffraction limit. Millimeter is actually very short for the radio wavelength. The first image in the first slide that I have shown was done at the frequency 2 orders of magnitude lower at about 2 gigahertz. So this is as far as we can go. The atmosphere is preventing us from doing much better than that. We astronomers would be very happy not to have the radio astronomers, not to have the atmosphere, but kind of there are other voices in the community that consider that atmosphere is actually useful for other purposes. So this array of DHT is more complicated than it looks from this slide, because there are subarrays which themselves are connected element interferometers. So there are 2 arrays like that, and I will be talking mostly about this one, about ALMA, the most powerful radio telescope we have as a humanity at our disposal. Now, think about this Sagittarius A star. It is a black hole that is doing something. I will show later that it varies on time scale of minutes. So think of it as a movie. There is a movie, something is going on. Now, if we use this EHT instrument, we have the resolution necessary to see like the pixels of the movie, to see what is this movie about, but we have to wait. We rely on aperture synthesis through the Earth rotation. We can only synthesize 1 image per night. One day, if we have a better array, we could maybe make movies that we make snapshot after snapshot. But for now, we make sort of the average movie. So we have this movie, something is going on, things are changing, and you average them in time. This is what Event Horizon Telescope can provide you with. Now, what ALMA alone can provide you with is different. It is, ALMA doesn't have the resolving power to see the structure of a movie. So it kind of averages it to a single pixel. Now you have a single pixel movie. It's boring, maybe, but you have the dependence in time. So with ALMA alone, you very carefully sample the time, but you do not resolve the feature. So we kind of have these 2 limits at our disposal. Seeing the average movie, the average in time, but resolved in space, or averaging entirely in space and seeing time variability. Now, this 1 pixel movie is what astronomers would refer to as a light curve. And actually, it turns out that we astronomers like light curves a lot, and we learn from them. So in the movie analogy, you can imagine like, okay, there are spikes of brightness in time, and something is going on there. Maybe it's an action movie, maybe something is exploding. If it doesn't vary too much, well, maybe no explosions. Maybe it's like a romantic comedy, for instance. So we will try to figure out what kind of a movie is Sagittarius A star in a minute. This slide is a very useful device to explain to you why we cannot make a movie snapshot after snapshot. Why do we care about variability during the observations? So the way this slide works, and I will play it in a second, is as follows. M87 is 1,500 times more massive than Sagittarius A star. So the time scales around the black hole, how quick the things evolve, scale with that factor. Characteristic timescale for M87 would be a couple of hours, say 9-10 hours. Now this is about as long as it takes us to synthesize a single image. So here is a human clock, and I will play the movie, and you will see how much M87 changes in a timescale of about 9 hours of our observation versus how much Sagittarius A star changes during the similar time. All right. So the clock is ticking, 1, 2, 3, about 1 second per hour. This guy is barely moving, so we can assume that it's a static image. We don't have to worry about intrinsic variability. This guy is changing as crazy on the time scale we are looking at. So we have to worry about these dynamics. And this is why it's difficult, more difficult, to make an image of galactic center than M87. This is the reason why EHT published M87 a couple of years before being able to push out the results about Sagittarius A star. Couple of remarks. This is a bit technical, and I will not go into details too much. But just to show you, let's say that this is a Fourier transform of this single snapshot movie. And let's say this is the time dependence, a single pixel movie changing in time. So this is our light curve from ALMA, and this is our EHT, say, average data. Usually when people give you talks about this business and Sagittarius A star, they will focus on this part. I try to stress a little more this time resolved part, mostly for the sentimental reasons, as I was in charge of this part of the analysis for the Event Horizon telescope. So what I will play to you now is the only movie of Sagittarius A star we have published so far. And this will be this sort of a single pixel movie. So the way this movie works, this is mini-spiral, once again. It's static, it doesn't change. This is parsec scale feature, many parsec scale feature. It doesn't change in minutes. But here is our single pixel, and this guy will be changing during our observations. So, yeah. Is it an action movie? Difficult to say, but maybe we'll have some more things to say about it. Clearly, there's something going on. The amount of radiation you see is changing by tens of %. To get this, again, you have to have EHT. You cannot rely on ALMA. This is the ALMA image in the background. This is the EHT averaged image. Now, we have 3 nights of data with ALMA available. And on 2 of those nights, we already published the individual images of resolved feature, as well as a single image averaged across 2 nights. However, we did not touch this guy. This is one day, April 11th of 2017, where we realized from Chandra observations that there was an X-ray flare just before the observations of the EHT. So our observations start here, and this is the blue is the ALMA light curve. So what we noticed is that on this day, there is more variability, more relative variability, and clearly something different could happen in the resolved system. So because we didn't want to have too much interesting things in a single bunch of papers, we decided to postpone the analysis of this guy. So this analysis is actually ongoing. We don't know yet how the Sagittarius looks like during the energetic flaring event. However, I have my suspicion. I will share this suspicion with you. Maybe it looks something like that. Well, X-ray flare is some explosive event. There is a X-ray radiation changing by order or 2 orders of magnitude. So this is totally unauthorized, and I don't know if this is what we will see. Hopefully, in a matter of short few years, we will learn about how this feature looks like during the flaring event. What you can learn from light curves, though, is that generally EHT is more like a romantic comedy after all. Even more so in a sense that our predictions for amount of variability overestimate the variability. So what I'm showing here is a certain method called structure function for characterizing variability as a function of time lag. So here are slow changes, here are fast changes. And if you integrate it, you would get something similar to standard deviation or square variance, really. These are the models from Frankfurt group, the previous group of Alejandro here. So they made a bunch of fancy general relativistic MHD models on which we measured the amount of variability, how much light curve of such model would change in time. That's what we get. And that's what we get from the data constraint. So actually, it looks like the Sagittarius A star is, I don't want to say more boring, because romantic comedies can be great. However, it is not as explosive, not doing as many things as the models predict. Only on a flaring day. On the flaring day, this variability jumps, and it would be kind of consistent with GRMHD models. But does it look like GRMHD models? We are yet to learn when EHT concludes the relevant analysis. However, well, we started calling that discrepancy, I don't think I put it here, but variability crisis. It's kind of nice and strong sounding wording. We don't know what is the cause. This is an interesting avenue for theoretical investigations, and many people are actively working on trying to explain what the heck are we getting wrong? Why is the real thing less variable than our best guess numerical models? I want to dwell on the light curves just a little bit before talking about movie averaged in time and not averaged in space. What else can we learn from the light curves alone? So one interesting diagnostics that people use is the spectral index. So this is a synchrotron emitting source. If you have a uniform parcel of gas emitting synchrotron radiation, it will be optically thick, meaning not transparent at low frequencies, and transparent at higher frequencies. And spectral index is a derivative of this spectral energy. So if you are around zero, meaning you are somewhere around the transition between transparent and non-transparent. Why are we interested in establishing transparency of the source? Well, if EHT wants to say that we see all the way to event horizon, it's better that it's transparent, that it's actually we don't see some kind of photospheric feature above the event horizon. So this test is interesting, but inconclusive, because we are somewhere at the transition region. However, interesting feature that happens on the flaring day. So here you have a flare. This is the time location of the Chandra X-ray flare. And this is the spectral index resolved in time. We can resolve spectral index in time. These guys are day averaged because of the power of ALMA and amazing sensitivity of ALMA. So you can see that spectral index is around zero, but immediately after the flare, it went down. So it kind of became less optically thick. So it is consistent with as if we put something bright, and very transparent into the system. And then whatever this thing is, on a time scale of 2 hours or a couple of hours, it disappeared, and the spectral index returned to a value around zero. I will try to explain what I think this feature is in the next slide. But before, one more argument in the battle of transparency, do we see all the way to event horizon, would be this plot. So what this plot is showing you, we have ALMA bands of frequency between 212 and 230 gigahertz, so it's kind of wide enough. If there is a photosphere, the location of the photosphere would depend on frequency, because transparency depends on frequency. So it means that if we see some disturbance, and if we would compare the timestamp of this disturbance between lower frequency and higher frequency, we would expect to see a time lag. So at lower frequency, the features should happen only later, once the disturbance propagates to the more outer photosphere at lower frequency. However, despite the fact that ALMA resolved these features in seconds, so we have extreme good time cadence, we see no delay. What it means is that if there is a disturbance, the location of this disturbance is the same for both frequencies. It must be co-spatial. It must be transparent. Both signals come from the same location in space. So this is a good argument for why we think we actually do see all the way to the event horizon, even without relying fully on the interpretation of a donut. So this is very supportive for the EHT claims. Now, because I do want to advertise my own work, like people love to talk about their own work most of all. So the interpretation of what I think happens after the flare, what is this weird, bright, but very transparent feature introduced to the system? I think it's a hotspot, or what we call hotspot for the lack of detailed understanding of what this feature actually is. Such features were observed in near-infrared by the gravity group. This is the same group that receives Nobel Prize for tracking the motion of S2 stars and finding the mass of the central black hole. And what they saw, apart from the astrometric motion, because they actually see a feature moving around, they also see peculiar loops in the polarimetry. So if you consider linear polarimetry is it's a vector, so you can plot it one component of the vector versus other component of a vector on the plane. We call this plane QU because QU are these two polarization components of a vector, and they saw these peculiar looping features coexisting with the astrometric motion that something is actually going around. And they started talking about hotspots going around Sagittarius A star during energetic flares. This is important that it should only happen during energetic flares. And this is what we see in the ALMA data in a similar convention where here and here are two components of the polarization vector. We also see this sort of looping features, but only after the X-ray flare. So we have an association between high energy event and behavior at radio frequencies. So of course, it's kind of natural to try to derive the similar interpretation. And it's consistent with this nice spectral index argument, because if this feature is a very hot parcel of gas introduced into the system, if it's very hot, it will be bright, but it will be transparent because hot features are generally more transparent. So it kind of works with the spectral index argument. And when it's a transient feature, it seems to disappear after like 2 hours, which is exactly when spectral index seems to return to its normal state around value of 0. So of course we build like a toy model to try to explain data a little bit more quantitatively, and we figured that, well, we think that the feature looks like that. This is a toy model, once again. So the only thing this model has to do with reality is the estimated radius. So where this feature is, that it's not on a very large orbit, it would look like that. And the light curve, how bright is this feature, also comes from the model. The geometry that it's a nice circle or a nice Gaussian blob is totally made up. It most likely doesn't look that nice as this simple animation. But who knows? Maybe once we get to making movies of Sagittarius A star, maybe we'll see something like that after the next X-ray flare that we catch. Okay, so I think I'm done advertising my own research. I think I will have one more slide to comment on papers that I led. But now I would like to tell you a little bit about what are we doing with this large collaboration effort from the Event Horizon Telescope. So first of all, like how do we make those images? How do we ensure that we see the thing that has anything to do with reality? So there's been a lot of thinking about that and a lot of effort to establish reliable pipelines for data imaging. The important part of that, I will actually click through that slide and then I will be talking about different parts of it. Oh no, too far. And now I have to start again. So I will try a different approach. Let's look at this step. Blind imaging with the feedback to the data. We always have problems with the data. It's a complicated observation, the very long baseline interferometry. There are unidentified issues with the data. So the way we approach it, we give blind imaging challenges to people and they report, oh look, this looks weird. My model don't want to feed this data and it looks weird to me. Can you double check that there was no problem with this particular telescope at that particular time? And when the data teams are looking into that, and more than often it turns out that it's a data problem. So this is our approach to assure the data quality. When you have a bunch of different methodologies for creating the images, However, you cannot just invent new methods and not validate them. So the way we approach the data validation is a part of it consists of asking a bunch of synthetic data tests. In particular, we want people to image different structures that could be misled for a ring. In Fourier domain, it turns out that you can mislead a disk or a double with the ring. So we don't want any of the algorithm to, when given a double, a synthetic data set of a double, to produce a ring. That would be extremely disturbing if our algorithms were able to recover a ring from the data that doesn't look like a ring in the image domain. So there's a lot of effort to ensure that the algorithms are not biased into particular image domain morphologies. And of course, there is this step of validation. What does it mean for the algorithm to do a good job? Well, first of all, it must return an image that is well consistent with the data. But it's not, turns out that it's not enough. There is a lot of messy images that can be consistent with the data and don't look anything like anything. So another criterion would be that if your algorithm has a bunch of hyperparameters, as algorithms have, if you change any of them just a little bit, does your entire structure collapse? Do you get something entirely different with a very slightly change of imaging parameters? If that's the case, then we don't trust your result. We want the result to be stable. We want them to be able to reproduce them with small changes of the hyperparameters. So it excludes another batch of different variants of algorithms. Now, what I will show you now is kind of the animation of what we do with the process once we have the variants and algorithms that pass those a priori tests. Right? So now we have algorithms that should work fine on synthetic data, don't seem to be biased. What can we do with them when we apply them finally to the real data? So you can see that we will get a bajillion of different images in that way. This is not a unique process to recover the structure of the source. This is Sagittarius, this is M87, the same procedure just for comparison. So how do we choose from this bunch of different variants of algorithms? Well, we took an approach of clustering them through machine learning methodology into clusters. So this is just morphological comparison in an automatic way, and each of the images can be classified into one of 4 sets. Then all these sets have their frequency of how often they appear in the reconstructions, right? You can see 3 of them actually look like a ring, but there is one that happens rarely, not very often. It's not really a ring morphology. So now we average those clusters with the weights corresponding to how often this cluster appears in the data. And this is how we obtain the final image, which we say, therefore, should be a nice representation of the features in the data. We're not saying in that way that it is really a perfect image. We're not saying that if you looked at Sagittarius in any particular moment, you would get exactly this. But what we are saying is that it is the most representative image domain interpretation of this Fourier domain data that we have collected. Some highlights from this imaging process. I think the one important comment is that vast majority of these reconstructions, as you have seen in this previous image, actually exhibit a ring morphology, and this diameter is important because this is a prediction or approximate prediction of general relativity that we should have 50 microarc seconds for the black hole of the known mass and known distance. What I want to talk a little bit in this last couple of minutes is the polarimetry and what do we actually learn from theoretical perspective through these images. So this is a very recent update that we have made images with polarization. Now, there's been a lot of confusion in media and also in scientific community about what the heck are those hairy patterns here. So these patterns are so-called wind plots of the polarization vector. So at every given point, a polarization vector would be tangent to these curved features. Right? This is not a magnetic field structure. It's a little different thing. So, and also it doesn't imply that we have resolution like between hairs in this plot. It's just shown in that way. So we super resolve it for the visualization purposes. Nonetheless, if you have asked me where is the polarization vector here, at this part of the image, I would tell you, yeah, it's tangent to this windy structure. Right? So having explained that, why is polarization so interesting? Why do we want to study this vector of polarization so carefully? Well, it boils down to this fact. The polarization vector is a cross product proportional to the cross product of the magnetic field, the direction of the magnetic field line, and the viewing, let's call it the wave vector, but this is actually a vector tangent to the propagation of a photon. Okay, so now if we were in the Newtonian world, that would be amazing, first of all, if we were in the Newtonian world, but then what else would happen is we would be able to see the pattern of vector P, the guys that are tangent to this hairy pattern from the previous slide, or these guys, the ticks, and we could rotate them by 90 degrees because of perpendicularity implied by the cross product, and we could say, okay, now we have a magnetic field direction. It's not so simple in the Einsteinian world with relativity theory. Well, the reason is this equation only holds in the frame of the emitter. So if you have a parcel of gas emitting and pushing through the magnetic field, the angles will depend on the velocity of that feature. This is the special relativistic aberration. So it will look slightly different. Then another thing is that in the general relativity framework, it's also not a straight line. The photons do not go on straight lines, so this k vector will be different for the emitter, and it will curve along the way, and it will look different from our point of view. This is a vector tangent to the trajectory of a photon. However, it turns out that for the toroidal geometry of magnetic field and radial geometry of magnetic field, this simple heuristic, rotate by 90 degrees, actually marvelously work pretty well. So these images include relativity in them. Here you have toroidal magnetic field, so magnetic field goes around the black hole. This is a face-on view of the black hole. And you can see that the P vectors, the polarization is radial. So the magnetic field was azimuthal, the polarization ticks are radial. So 90 degrees difference. So marvelously, despite of relativity messing up things a little bit for us, the heuristic, the intuition works fine. Similarly for the radial magnetic field, but now vertical magnetic field is kind of a pickle, because you look into the black hole face on, you have magnetic field vertical, meaning it goes toward you, and you have your line of sight, which also goes toward you. So you have vector k and b. In Newtonian world, they would be just parallel. So the cross product would be zero. But that's not what we see. We see kind of characteristic twisty pattern with a presence of vertical magnetic field. And this is what how relativistic aberration and curvature of space-time is manifesting partly at least in that way. So this guy is difficult to understand with Newtonian kind of reasoning, but we calculate it and we expect this twisty sort of pattern with presence of vertical magnetic field. I said I would get back to advertising my own work, so this is the last time I do it. I will be talking about the collaboration work afterward. But there is one more thing to mess up our simple understanding of, well, take the P vector, go perpendicular, and there you go, magnetic field lines. This one last thing that messes up our intuitions are the Faraday plasma effects. So if you have radiation propagating through plasma with the presence of magnetic field, your polarization vector, the plane in which light waves are oscillating, will be rotating. We call it Faraday rotation. It's proportional to the density, which is NE, and to the parallel component of magnetic field. Interesting thing, this is parallel magnetic field component, parallel to the line of sight. This is a different component than was important here, because the cross product is telling you that you only care about the perpendicular guy, the guy perpendicular to the trajectory of the photon. So it's probing a different part of the magnetic field structure of the source. Now, why is that a pickle? Why is that a problem for us? Well, it turns out that there is a large Faraday rotation measured toward Sagittarius A star. It is about 50 degrees. 50 degrees is actually changing our interpretation of the system, because we don't know, should we, apart from this perpendicular, should we also account for this 50 degrees from Faraday rotation? And to confuse people even more, I wrote a paper this year that measures the rotation measure at two different wavelengths for the first time. At 3 millimeter, the blue curve, and 1 millimeter, this is the EHT wavelength, and it turns out that rotation measure is different, measured at these two different frequencies. It implies that the Faraday screen is complicated. It's not an external screen, it's not an internal screen. It happens, it's some kind of mixed Faraday screen. So this is something where we have to learn more about the system. This is a parameter that can confuse our theoretical interpretation of the polarization results. I obtained this interpretation based on what I call an onion model of Sagittarius A star, because the model is extremely simple. It's a spherical symmetry, and different wavelengths are emitted from different layers, just like the onions. Onions have layers, famously. I am a little bit behind, but I want to comment at least on this part. Everybody wants to be Bayesian. We all are in a sort of a Bayesian frenzy, and the analysis that is fully Bayesian seems to be more appreciated than the analysis that is kind of done with the frequentist sort of set of mind. So I split this last part of the talk into two subsections. One is the inference that we do on MHD, so on the astrophysics, the physics of plasma, the physics of gas, assuming that GR is a correct theory, so we interpret using Kerr metric numerical models. And the next part of the last part of the talk that I will probably not be able to talk to you about would be the other thing. So we assume that we understand MHD, magnetohydrodynamics, we assume that we understand astrophysics. What can we learn about the gravity theory under these assumptions? So the way we interpret, we try to learn about astrophysics assuming gravity theory is by constructing a huge library of numerical models, very advanced general relativistic MHD models. And Alejandro is one of the people who developed these big libraries of models. There are a couple of dimensions to these models. One of these dimensions is the strength of magnetic field, which affects the configuration of the system. We generally have strongly magnetized models that we refer to as MED, magnetically arrested disks, and we have weakly magnetized solutions that we usually call standard and normal evolution kind of systems. We call them sane. We test different values of black hole spins, how fast is the black hole rotating. We have a very, very simplified prescription for the heating in plasma, how hot are the electrons with respect to ions, which is, we use pretty much a single parameter just to quantify this difference. We test different inclinations because we don't know what is our viewing angle toward the Sagittarius A star. We do some less systematic tests with non-thermal electrons. Again, Alejandro is a great expert in that part. And for the polarization analysis, the recent one published earlier this year, we add orientation of magnetic field as another model parameter. The reason is that all those Faraday effects actually do depend on the sign of magnetic field. It's not the case for the motion of fluid, it's not the case for the pure MHD. But for these Faraday plasma effects, the direction of magnetic field unfortunately matters, doubling our size of this huge library and forcing us to consider different orientations of magnetic field or polarity of magnetic field. Now, we have all those models. We want to evaluate them against the data. And for that reason, we select a bunch of criterions, like measurables from the data. Some of them depend on EHT, like the diameter, observable diameter of the ring. Some of them come from different frequencies, like limits in infrared and in X-ray. Some of them depend on this light curve, and this is this variability crisis that relates to that. And once we have polarimetry, we add more constraints from the average linear polarization, from the average circular polarization, and so on. We have a bunch of new constraints. So whatever is in red will refer to these new things that we have added this year. So this is a very beautiful animation that shows you a collection of the models that we start with, and then we apply different criteria to rule them out. Do they agree with the data according to particular criteria? So this is how they behave. Now let's start applying constraints from the size with the Event Horizon Telescope. Any second now? Size. It only removed a couple of models from our collection. Now the shape, some of them are less circular, some are more circular. We would generally expect a difference. Spectrum, different constraints at different frequencies, and we're pretty much left with very narrow number of models. So to illustrate that on the set of possible solutions, we have something that we refer to as pizza plots. These pizza plots show you MED models, so magnetized, non-magnetized, different spins, different inclinations, and different values of this plasma parameter. And this, let's not dive into details, but this is just to show you that all the constraints applied preclude most of the solution, apart from these just couple of different models. We call them best bet models for that reason. You can also notice that light curves variability actually kills those good models. So we may understand the mean structure of the image, but we still have this variability crisis, this kind of a problem that it just doesn't vary as much as the simulations. All right, so this is just a summary of the astrophysics. What is important are these general conclusions. We sort of think that the conclusion about the strong magnetic field is robust. We really think we see MED model, the model with the strong topological magnetic field, not with a weak turbulent magnetic field. This is the one conclusion that we are really certain about. There is a bunch of other conclusions that are related to our validation of these models, like low inclination of the system, that we look at something not edge-on, but almost face-on, or about 30 degrees. This is, by the way, consistent with the light curve analysis and this hotspot thing that I did separately. So we have at least two different ways to argue for low inclination. We can argue for the strong component of the vertical magnetic field from the topology of magnetic field, but also from the hotspot analysis. And if you add polarization to that business, it turns out that the best bet model actually survives additional constraints from polarization that we didn't consider earlier. There is a caveat to it, however, that it depends on this Faraday screen nature. So what we need to do now is we really need more observations and we really need more careful analysis. What the heck is going on with this Faraday screen? Where is this Faraday screen living? Is this coexisting with the zone of the emission? All right, and I think I will end here because this is like a big different topic. So let's not dive into that. Let's conclude here. Thank you very much.
Thank you very much, Maciek. So we go to the questions now. So are there any questions here in the auditorium?
Hi, very nice talk, thank you. Is there any reason as to why the GRMHD models overproduce variability?
Oh, that's a
The physical reason.
Yeah, that's a wonderful question. Many people are considering that, and there are many different explanations that were already proposed. The theoreticians actually try to argue that perhaps the interpretation of the data is wrong in a sense that there could be milliarc second extended emission in Sagittarius that we are blind to because it's between the scales probed by ALMA and between scales probed by EHT. If there was additional flux at extended scale, then in our denominator, to calculate this relative variability, we would have more stuff in the denominator, and it would decrease the explanations. I don't think that's true, because we have a couple of ways to support that there is no extended, no important amount of extended flux, lower frequency observations, and so on. So there are theoretical attempts to explain that. One is related to this naive prescription of electron heating, that perhaps if the heating of the electrons was done self-consistently, it would change things. And some early results show that it changes, but like 20%, which doesn't seem to be enough. My favorite explanation is related to sort of non-locality of this emission, so that the heating doesn't take place exactly at the same spot as the emission, which all GRMHD models imply in their construction. And if you have this bunch of electrons kind of going around and being heated somewhere and emitted elsewhere, that would, this is very hand-wavy understanding, mind you, but it would act as sort of an average. So I would imagine that it would dump this variability by sort of averaging, that there are many scales, many different locations involved in the process.
Okay, thank you.
Another question here.
Sorry, before, maybe I can comment something quickly related to the models. It's also because our models are very simplistic, no? We have ideal MHD, and we have no viscosity, we have no resistivity, so we have to include a lot of physics into our models, no?
Absolutely.
Apart from what you already
Assumption
explained.
of ideal MHD would be like another thing. We know that there are non-ideal MHD effects playing a role, like reconnection, and this could be the reason, but the honest answer is that we don't know, and we are excited to learn what is the cause of that discrepancy.
Yeah, but if you include reconnection, you're going to have much more variability in that case.
So this is actually not obvious, and I must say I don't fully understand
you're going to be creating flares, whatever the reconnection is taking place.
But you know, we have flares anyway. The reason is that there is always some kind of subgrid resistivity related to discretization. We do see flares, even in resolution that do not resolve the...
Yeah, but in ideal MHD, you're not going to have flares due to that.
Not in a physical way, not in a proper physical way. Yeah, if it increases the variability, that's actually bad. But you may be right. I'm actually not aware of what is the similar measurement of variability from the very high resolution models that resolve the current shift and reconnection zone.
Yeah,
maybe Alejandro knows. He's smiling.
Direction. Yeah, it will go in the
yeah, it could be going in the wrong direction.
Yeah. Anyway, can you go back to this blob that you were showing that was going around?
Oh, sorry, I'm going in the wrong direction. I'm revealing the part I'm not sure.
I didn't understand what's the relationship of that. Oh, you passed it. Yeah. I didn't understand what's the relationship of that blob with the X-ray flare that you showed.
Okay, that is a wonderful question and gives me a chance to comment on it. So this touches what we think is really physically going on. And mind you, this is an interpretation, and people will not necessarily agree. So if we had reconnection properly accounted for, and if we have these flux eruption events, what is forming in this system, and this is shown in a number of GRMHD simulations, is what we call flux tubes. Flux tubes is what people refer to, they call it an exhaust of reconnection. So it's something that happens after the reconnection, after these plasmoids acting and going in the equatorial plane or in the current sheaf on the edge of the jet. But when a macroscopic feature, plasmoids are generally small features, the macroscopic feature of a flux tube forms. In particular, in the simulations, high-resolution simulations by Ripperda from 2022, we really get these, columns of low-density gas heated with reconnection, with predominantly, tangled magnetic field, but predominantly with a vertical component and other components tangled, which orbits together with gas around the black hole until it's being torn apart by shearing, by magnetic Rayleigh-Taylor or whatnot. It's a transient features. The question is, can this feature be bright on the top of having other qualities that this hotspot should have, meaning vertical magnetic field, being hot, low opacity? This is not clear because we don't know what to exactly, how to paint electron emission, because we don't know how exactly is that heated. But our interpretation is like this, that there are these macroscopic flux tubes, they act like transient orbiters. It seems to be at least partly confirmed by GRMHD simulations, but would they be actually bright enough? I don't know, and it takes probably kinetic simulations with radiation to really make significant progress there.
Yeah, okay, thank you. And one final question. If we go to the Faraday rotation part that you got, you have different angles for two different wavelengths, right?
That's right. Let me, okay, we have the slide.
And if you assume that this is related with the Faraday screen in the place, then you're going to have problems trying to explain this. But Faraday rotation will be operating outside the screen. And I don't know if that might explain this difference.
Okay, so if the Faraday screen was entirely independent of the emission region, if that was fully external Faraday screen, then the measurement of rotation measure would be the same at two frequencies. So this is exactly, and this is a common picture. Yeah, this is the common picture actually that people had in mind. So this paper and having a measurement at 3 millimeters and 1 millimeter, we know from VLBI where are the emission zones. The emission zone from 1 millimeter is where the torus of the EHT lives, which is like 4M just above the event horizon. The size of the feature at 3 millimeters is about 10M, so also just 5 Schwarzschild radii. So now if the screen is fully external, both should experience same rotation measure, and because there is a factor of 2 between them, my argument is clearly half of the Faraday screen lives between 1 millimeter onion layer and 3 millimeter onion layer. So this is a puzzle. This is a new thing, and we need, first of all, we need more observations because these are first 3 millimeter high quality light curves used for this research.
¿Hay alguna pregunta en Zoom?
En Ensenada.
Sí.
Hi, Maciek. Thank you for the talk. I have a question. From the circular net polarization, can you measure the longitudinal magnetic field? And the other question, which is related...
Can you measure what from circular net polarization?
The intensity of the longitudinal magnetic field towards you. And the second question is, when you talk about MAD and sane models, how much in intensity of magnetic field are we talking about?
Yeah, okay, two wonderful questions. Let me try to tackle the first one. The reason why it doesn't translate in any straightforward way to a simple model, simple argument for the strength of magnetic field is because a circular polarization emission is a complicated beast. If we were to assume that it's all intrinsic emission, we could have a toy model to translate into the magnetic field strength. However, in these numerical models that we try to explain things with, the Faraday conversion process, which is a process converting linear polarization into circular polarization, matters to complicate stuff. So actually, the translation to magnetic field strength is not straightforward. So that is one problem. And Could you repeat the second part of your question?
Yeah, it was just about the intensity between.
Yeah. Okay, thank you. Right. So, yeah, we have a prediction based on toy models, like one-zone model, a synchrotron bubble model, which tells us that near the event horizon, the magnetic field is tens, no more than 100 Gauss. And it turns out that it agrees also with these more fancy GRMHD models, what they give for the power of magnetic field near the event horizon. Now, 100 Gauss is not impressive at all for people like studying magnetars. They would kind of be very unhappy about us calling this strong magnetic field. However, notice that we're talking about very low mass accretion rates. So the magnetic field strength comparing to the strength of inertial forces that will depend on how much stuff is there are dominant. So when we say that we have strong magnetic field, we mean tens or 100 Gauss, but this is enough to be dominant and rule the dynamics of the gas. So it's strong in relative sense.
Okay, thank you.
Una pregunta más aquí. Creo que Irene tenía una.
How do you know the location of the hotspot? I didn't
Yeah.
understand.
Okay. So let me just give you a few words about this model. Okay, so we build a toy model. The toy model is well, there are different amounts of toyishness in this model, but let me talk about the simplest model. The simplest model is just a polarized point source going around a Kerr black hole. And now, because you have Penrose-Walker constant in a Kerr space-time, you know, if you know polarization and emitter frame, you can calculate how it would look like parallel transported along geodesics to the observer. So basically, this is all semi-analytic work in this most toyish variant of this model. To have the exact geodesic, you do need to specify where is your hotspot. And to know how the polarized vector looks like in an emitter frame, you need magnetic field for this perpendicularity reason. So we just test a bunch of models and we fit to the ALMA polarized light curves. How would it look in the distant image domain plane? I will just add one more comment. Blue is data in this plot. The dashed line is a point source model. The continuous red line is a Gaussian model where we actually, so it's not a point source, it's actual macroscopic feature orbiting, where we also account for the radiative transfer. So we actually solve the radiative transfer from this Gaussian bubble. And you can see that both are toy models, of course. There are other forces at play. We make up the velocity pattern, we just assume it, or we test different variants. But you can see how close they are. So this semi-analytic model is very similar to like a small Gaussian bubble where we account for the radiative transfer.
One more question here.
Thank you. I have a question about the polarization. Sorry. Can you go back to the slide of the last question, please?
For what?
About the polarization.
All right. Sorry, it's a lot of clicking, but we're getting there. So this was the images. More?
More.
Okay.
There. I have a question about the fractional polarization, about the mechanism responsible of depolarize the light. Because the fractional polarization in that figure, the maximum is 0.5.
Well, from the colors, it's like 30% in this most polarized region.
Mm-hmm. Yeah. My question is about the mechanism responsible of depolarize the light.
Okay, so synchrotron radiation is naturally polarized, and the fraction of polarization depends on a couple of things, including the power index of the electron population. So what is the energy function of the electrons? However, this peak, what you would get from the uniform zone of electrons emitting synchrotron radiation is like 70%. This is like the natural value. Now, in observations, you are not expecting to get 70% for many reasons, like resolution reason. If you bundle up different zones, they will average out. It's a vector. Vectors are adding coherently. They will generally may tend to destroy one another. You also don't look at 2D distribution. You look into depth. This is a 3D feature. So stuff behind you may experience things differently than it's just non-homogeneous. Then also Faraday rotation through this gas. The stuff more distant to you in this 3D projection will experience different Faraday effects than this guy here closer to you. We call it Faraday depolarization. So mixture of resolution effects, Faraday depolarization effects, and so on cause you that you never measure this 70%. 30% is actually a very strong fractional polarization. And it tells you that there must be a structure to magnetic field already. Because if it was turbulent, there were small zones with random orientation, it would average out. If it has 70%, it means across the beam, our resolution element is kind of like thickness of this ring, it's pretty uniform because it doesn't totally average out. So this is another argument for magnetic fields being like topological, not random and incoherent.
Thank you.
Okay, so we can thank Wielgus again for his fantastic presentation.
Thank you very much, and thank you. These were really good questions, touching to the point and allowing me to elaborate. Thank you.
So thank you, everyone, and see you next week. Thank you.